let's get started. There's a lot to talk about. So this talk is about I/O interface independence using xNVMe. And to give you some background about where this is from, let's start with that and then look at what we mean about I/O independence and how we see a way to solve that. Now, I/O independence, that's sort of the motivation for this is that sort of traditional storage is operating system managed. It's just reading and writing from your storage device. And usually the bottleneck has been your storage media. So on a traditional storage device, there's a very high media access latency, and they really do not benefit from parallel access. Then we got NVMe devices, a whole other story. That's relatively much lower media access latency, and where there's a very high parallel access benefit. So what does that mean for actually programming it? How do you utilize and get your commands, your data down to your devices? Well, one of the biggest challenges is in a typical operating system design, crossing the barrier between user space and kernel space. These have been synchronous primitives, and there have been optimizations to do more work with new syscalls. However, that still leaves the problem that in a synchronous mode, you always have to do your command, wait for all of the stuff here to happen. That's transferring data from DMA, crossing this boundary, doing the media access, and not until you're done can you start submitting the next command. So you become blocked while you're waiting for your storage to finish. Well, you can fix that by doing thread pool. The issue about a thread pool is that you are bound by the number of cores you have. So that just doesn't scale. If you're selling storage as a service or building a flash array, quite quickly you have way more devices than you have kernels to actually saturate to make use of your storage devices. So the more popular approaches are today using async interfaces, where what you can do is overlap your I/O. And basically, instead of having both the submission of a command and the completion of it in one function, in one syscall, you can split that up. So as soon as you have done your first syscall sending off your command, you can submit the next and the next and the next, and then do overlapping all of your I/O. Then when you need to check how did it go, did I actually submit? Well, that's where you can start checking the completions. However, that doesn't solve, and the latest edition that you saw in the previous talk describes some of the challenges and performance issues of doing these things. So there's a bunch of trade-offs in using these different interfaces. Currently, async I/O is some of the best thing we do have today. However, that doesn't solve all of the performance problems. That does solve some of the performance problems. But what we have today is actually also new innovations on the device side. We've been used to just having block devices, but today we have new stuff like zone devices that split up your block range, where you need to manage it, know how many zones there are, the sizes of them, and how to send I/O. That requires some additional commands that you need to send. And things are getting even more interesting. We now have KV SSDs, where the interface from the NVMe SSD is actually the ability to send a key value store directly to the device. And that can also be over a fabric, so over the network, you can talk directly to your device and send a KV store. And on the verge is now also computational storage, where you can actually load programs, run programs directly on your storage device. So these interfaces doesn't really fit there. And what you typically do then is go into kernel bypass. You have to drop all of these abstractions and run your user space driver or run your NVMe driver directly in user space in order to utilize these features. Or you could use like an ioctls syscall and talk with the NVMe driver in the kernel. However, that is very inefficient, as that is still a synchronous call, so you need a thread pool, and then you're back to the same issues up here. And the problem just gets bigger and bigger. So that's just for Linux. When you look at other platforms such as FreeBSD, even Windows and Mac OS, there are sort of the same challenges. And the issue is that it's also growing. So we've added now something called iouring command, which is actually pretty awesome. And I hope I have time to come back and describe what that is about. There's also now a new NVMe driver that you can use from user space. So basically with all of this, sort of exciting interface change. Well, we have like interfaces fluctuating from being operating system managed, complete kernel bypass. We've seen here on systor also, you know, the unikernel approach. How about breaking down the barrier completely? So there's a lot of ways that at the host side, the interfaces are changing. And with various trade-offs. And there's also the innovation going on the device side. So the question is really, how do you manage and leverage those changes in your I/O interfaces? And how do you really avoid the consequence of all of these things that enable you to talk with your device without being locked into one single system? You would either have to, for your system or your application, make sure that this runs on all of this, or be tied into the trade-offs of one single approach. So what we really want is this I/O interface independence, a way to separate us from all of the lower level concern by still having the control and not lose performance. So with I/O interface independence, what we mean here is the opportunity to change your I/O interface without refactoring the rest of your system. So to be able to go from running an SPDK NVMe driver to running IOU ring without changing your code. And it's our hypothesis that that should be possible, and at a negligible I/O cost of that. So by negligible, what do I mean there? Well, take a look at these numbers. So consider like there will be a cost to have this kind of I/O interface independence. So the question is really, how much are you willing to pay for that? So for instance, what else are you paying for? So in a system here, if you want to attach more than one NVMe SSD, eventually you're running out of PCIe lanes. Then you need a PCIe switch. The switch costs you 150 nanoseconds per I/O. If you route stuff through the platform controller hub, you can do an easy experiment of that. That will cost you 860 nanoseconds. And if you're routing your stuff through the operating system stack, that costs you around 1500 nanoseconds. So we can talk afterwards about this. There's some easy experiments that you can do that will show you these numbers. And then consider that the actual media access time today for fast NAND is 7000 nanoseconds. For regular client SSD, it's around the 60,000 nanoseconds. So negligible performance like trade-off would be something in the very low hundreds in terms of nanoseconds. Something where we're talking close to a PCIe switching should be even lower than that. All right, so coming back to these questions, is I/O interface independence possible, and what is the cost, and how do you manage and leverage all of these changes going on both on the device side and the software side for accessing your device? Well, that is where our answer is xNVMe. The idea of this project is to create a minimum spanning layer, having the minimum amount of software components to describe the stuff that you want to do. And the things are expressing commands, sending them to the device in a synchronous fashion, as well as in a non-blocking async mode to your devices. And it should encapsulate all of this. And so that's what we set out to do. And to give you a notion on what that looks like, let's browse through the API. So when you need to get access to a device, you need a handle for it. So you can enumerate a system. That system can be local, it can be remote over a Fabrics endpoint. And when it's local, here you see the command line utility using the API. It gets access to the user space driver, one version of the kernel interface for talking with your block device, and another way where it's running through the uring command interface. So you have that one API accessing all of the different system interfaces. And that's locally. You can give it another URI and you'll address a device on a remote endpoint. So you get that device URI. And with that, here's a couple of other examples, is basically the idea that all of this requires a bunch of different system interfaces. But when you program it through this API, you can use any of it and you don't have to be concerned about it. And although xNVMe is designed for NVMe, it's still the model works for traditional storage. So when you're developing, you can use stuff like the non-block devices on Linux, emulated devices, do all sorts of things that aren't NVMe. The model fits that as well. Sort of provides a transition from traditional into new and emerging storage interfaces that are based on NVMe. And so the general form is that it'll try and make a best guess at what kind of system interface you want to be using. But if you want to control that explicitly, you can also do that by just flipping these different configurations. And that's all you need to do. You don't need to change any more than that. So another thing that's worth mentioning are the buffers. So payloads on NVMe are usually something called PRP list and SGLs. So the question might be, why aren't we using that here? But we really want to have some form of uniformity, a way to address and use different interfaces, both operating system supported and kernel bypass. So by supporting contiguous buffers and vectored I/O, which is what you typically see in your storage APIs, well, then we can have an API that'll work both with the kernel and without a kernel. And you then need to call this buff alloc to get your memory allocated. What this takes care of is all of these other things that you need to do for an I/O buffer. It needs to be page aligned. If it's supposed to run with a user space driver, that needs to be DMA transferable memory. And for block device I/O, it needs to be aligned to the block sizes. All of these requirements for allocating your buffers correctly. There's a function called to take care of that. And then for sending your commands, there are two functions, pass and passv. There are two because one handles vector payloads, the other handles buffers. The interesting part is really the command context. That's where we encapsulate the submission of the command and the completion of a command, along with some auxiliary information on how to take a path down here. And it's probably going to be a bit hard to see, but you then construct a command here in your C library where you just set the opcode that you want to send, the namespace ID, and what we're sending here is a zone append, and telling it this is the zone I want to write to, and this is the number of bytes. And then you call this command pass function. So this will construct the command and send it down the stack. And it's separate from being synchronous or asynchronous. So the actual construction of your command really doesn't care about which path it's going to take. And the way you control that is getting one of these command contexts. And if you want that to be here on the blocking path, well, then you get it from the device. Set it up as you saw in the other example, and then you call pass. When it's done, you can inspect the completion results. Doing this in the async fashion, well, that requires a bit more work because you need a queue to stuff into. So you need to initialize that. With a queue initialized, the submission is actually completely the same. You're just getting the context from a different source. Instead of the device, you're getting it from the queue, and then you pass that command down. Then you need to check how did it go with my I/O? And there you have two options. One is just taking a quick look, how much has been processed, and get the results for those. And every time something is completed, you get an invocation of a callback function. So this is actually your typical async callback interface, encapsulating over here SPDK I/O queue pass, I/O controller ports, I/O control blocks, and all of the different interfaces currently available. And you can also sort of in a barrier style here at this point say all outstanding I/O on a queue. I want to have that as a synchronization point, so here I'll be blocking until the queue is empty. And that's actually all there is to the API. Those are sort of the minimum things that you need to do to get a handle on your devices, allocate memory for them, and call functions in both a blocking and a non-blocking fashion. And you can have some more details at on the website where it's the API is documented. So to have a closer look on the abstraction level, so the stuff with commands, queues, and all that sort of encapsulates all of these components, including something like the SPDK NVMe driver. SPDK is a pretty awesome project. It has a lot of stuff. It also has ways to abstract these lower level things that they call the SPDK BDEF. That's the block device abstraction. And it too can use, for instance, xNVMe as the core for sending it through the operating system and use its own driver to send it through the user space driver. So that's sort of to give you a notion of what's the abstraction level. It's above the driver, but just only above the driver, providing those primitives. You can then use that to build the command sets for new device interfaces. With that small amount of code, you can make new functions for getting your device to do stuff, and that sort of provides it as a building block for your applications and for your experiments. So you can just write that in one single interface and you'll get access to all of this underneath. So let's have a look at a performance evaluation. And what we really want to do here is quantify the performance penalty. So how much are we actually paying to get this I/O interface independence in terms of latency? And we want to do three things, which is establish a baseline overhead, compare it to how it performs for the different I/O interfaces, and do a quick sanity check of scalability and see how it's doing there. And we're using just regular commodity hardware for this. And specifically for the device-sensitive stuff, we're using an Optane SSD, which has an access latency of around 7,000 nanoseconds. And we're using FIO, as that has reference implementations for all of the I/O interfaces that we're also using in xNVMe, along with the SPDK FIO I/O engine to use there as a reference implementation, which allows us to set up the same workload and to test the same workload on all the different I/O interfaces. And the workload is doing a random read spanning the entire device. That should mitigate most of the effects of, for instance, that might occur when you do reads at QDEF1. And one notion, as we also saw in the first talk today, the I/O interface behaves in a lot of different ways. We're especially interested in the most scalable way when we're comparing this, as that's where we get the lowest latency. That'll give us the best notion on what are the latency numbers when comparing it to xNVMe. So first off, for the baseline, the way to evaluate that is both xNVMe and FIO supports a null mode. So basically an I/O engine that doesn't do anything except for taking your commands and completing them immediately. So in FIO, that's called null. In xNVMe, that's called nil. It does the same thing. But that allows us to actually measure how many nanoseconds are we spending on average just for the software layer overhead of submission and completion. Now, the minimum is 8 here for null and 82 for xNVMe, and the maxes are quite high. That max latency is due to the setup that FIO does, which become part of the measurement. But it's actually not part of sort of an artifact of the devices or anything else. So that's why we'll just be looking at the average latency going forward. And the second thing is, what we can establish here is that we have a baseline overhead of 54 nanoseconds per I/O. That is sort of the cost of doing this. So let's take that further and look at how is it doing for the different I/O interfaces. So what we see on the plot here is on the y-axis is latency, and we have teamed up the reference implementation with the xNVMe implementation. Our expectation would be to see the reference implementation plus those 54 nanoseconds for the baseline, plus an I/O-specific encapsulation overhead. Now, this holds up for the IOU ring, that's the two ones here, where in the worst case, it's 136 nanoseconds in terms of overhead. On the other engine that you see over here, it's actually a bit lower, 129. So that's sort of what we would expect. That would be the ballpark numbers of doing actual encapsulation and seeing it all the way up and down. What is actually kind of surprising is that in all of the other accounts, the latency is exactly the same or less. And that might seem very strange. But one thing here is that most of these interfaces, except for IOU ring and SPDK, are interrupt-driven interfaces. And the reference implementations for interrupt-driven interfaces are that you give it a timeout, and that timeout is around 250 microseconds. What xNVMe does instead is just say 0, and when you just say 0, it'll return immediately. So xNVMe is using the I/O interface and basically polling on that instead of polling on a driver. And when you do that, you actually obtain lower latency than had you been waiting for the timeout and the interrupt to wake up your thread. So that's why. And for SPDK, the story is slightly different. It's two different I/O engines. The SPDK FIO I/O engine does extended LBA format, where it does a more generic calculation when it needs to calculate the offset in bytes into an LBA address, where the xNVMe one just shifts the address. Then there's a more generic calculation there for the SPDK I/O engine. It also taps in a slightly higher inside of the SPDK NVMe driver, where the xNVMe taps in at the lowest level, so there's shaving off a bit of cost for doing function call overhead. All right, that brings us to the scalability check. And for the scalability check, we just want to verify that this latency penalty is constant when we scale up the block size and scale up our I/O depth. So a perfect result in this case would be that the lines would just be running parallel to each other. So we did that here, and yeah, unfortunately it's a bit hard to see, but the takeaway is that it is a near perfect result. What you can see is the green line here. So the lines are parallel. This is the reference implementation of, the red is the reference implementation, and the other one is xNVMe. And it's lower due to that polling thing I mentioned before, but they are running in parallel. What's interesting here is that what you're seeing is the latency in nanoseconds as a function of I/O depth of POSIX AIO. So that's different from libaio on Linux. So with that, on FreeBSD, the performance is way better, way lower latency than on Linux. So that's just something that's sort of unrelated, but that's why it's deviating there. Where it is sort of failing is in the Windows case, and we've identified that as an issue in the implementation that doesn't scale well, that hinders or sort of increases our latency. So that's something to fix for future work. And when scaling the block size, it is actually near perfect results, so that's fine. We can basically just conclude that it doesn't degrade when we scale up. And the thing you see with the blue outlier here is that on FreeBSD, although the latency was better, it doesn't scale as well for when you increase the block size. All right, so conclusion on the performance. Yeah, we have a baseline penalty of 54. It's 129 to 36 on IOU ring. And for the interrupt-driven stuff, it's actually less, and same for the user space driver due to a change in the IO engine. And otherwise, the penalty is constant. And since I don't have a lot of time, but in the beginning I told you about IOU ring couldn't support anything but reads and writes. We've been working now for 2 years on enabling something else here. One thing is using KB drives and stuff like that to be able to access those from Linux, and then enable sending commands over IOU ring. So with that support in Linux, you can now actually enable that, all of these devices, as something that's managed by the kernel. And for xNVMe, there's no changes now in leveraging that new interface. Otherwise, we just added some Mac support because we got a new guy on the team that liked that, and a new user space NVMe driver. We had some users who wanted to play with Python, so we put that in. And we got this upstreamed into FIO, so it'll be ready with the next release. And we have patch sets for SPDK as well. So I think that'll be the summary. And check out the documentation, our repository, and the article. And I think that's it for me. Thank you.
We're running out of time. I've got a question. So, just very small one. So, basically, by adding this level of interaction, does it imply that you require all other developers of all those variety of APIs to interface with yours?
No, so we're on top of all of the other interfaces, so we're using them. They don't have to use us.
No, what I'm saying is that if I want to develop another interface, then from the current perspective, I would also need to interface with you, like BFS. Any file system needs to be interfaced with BFS, similar here.
No, so this is entirely in user space, so you don't have to, yeah, so it's managed out there. Yeah.
One more question.
All right, so let's thank the speaker again.
Thank you.